Hey everyone, welcome to the DC Python Meetup. I'm Alex Clark, President and Executive Director of DC Python. Today we have Eric Soros. Is that right, Soros? Soros. Today we have Eric Soros giving a highly technical talk, but still approachable. And he has an assistant with him. Before we get started, I would like to go around, have people introduce themselves, talk a little bit about what you do with Python. And if you don't want to do that, that's okay. I'm going to start, and then I'm going to pick someone else to continue, and we'll take it from there. All right, so I'm Alex. I do Python. I'm the President and Executive Director of DC Python, as I said. I'm also the President of AClarkNet, a software consulting firm focusing on open source. I'm doing one of these meetings per month, the last Saturday of the month, every month. So be here if you can. Thank you for attending. The organization DC Python organizes the events, and we rely on volunteers and donations from folks to perform these operations. So if you can donate, please do. I just put a link in the chat box. And I wanted to call out Jacob, who's on the call, who is also organizing meetings for DC Python. He's active this year, along with myself. We have some other organizers potentially putting together some meetings for you. And I think that's about it. I will pass to Eric to introduce himself. Then we'll go to whoever else wants to do the same, and then we'll have Eric start his talk.
Okay. My name's Eric Soros. I'm outside of Dublin, Ireland, and I have been working with Python now for 15 or 20 years or so. I'll cover a bit more later, but most of my work these days is either with Pillow, with outside consulting, or my day job is working with a company that does open data portals. So we are responsible for data.gov.ie, which is similar to data.gov in the US, where most of Ireland's public access data sets are cataloged and posted.
Great, that's awesome. I didn't even know that about you, and I've known you for 8 years. Okay, pick someone at random from the chat.
I don't know, it looks like Daniel's next on the list.
Hi, I'm Daniel Cavan. I work in Calverton, Maryland. Well, I work at home, pretty much. I'm working. I was signed up to go to the Python event, the convention in Pittsburgh, but it didn't happen in 2020. So I'm thankful for these groups to try to get caught up. I'm working with an API right now with Okta to try to do authentication, to send an email. We have a Radius implementation, so we didn't do it with SAML, so we don't go to the portal, the Okta portal, and we're trying to do when people get down to 10 or 5 or 3 or 2, 1 days left before their password expires, send an email to those users. So thank you.
Very cool. Pick somebody to go after you.
I guess Sergi on the bottom.
Okay, hello. So yeah, my name is Sergey. I'm work with Django for about Python Django for about 10 years. I'm stuck with Django and I really like that framework. Currently, I work in a company which do integration with automotive dealer CRMs, and we have a lot of data, and I'm interested in how we can optimize that data processing, potentially with the ClickHouse. So yeah, I'm really interested in that talk. Thank you. Should I also pick someone?
Yes, please.
Let it be David Jack. I don't know.
Yes, hi guys. So my name is David Jack. My day job is a financial analyst. I've been in corporate finance for over 20 years. Well, actually, I started learning Python, and so I'm not sure really if I hope I'll be able to follow you to some extent of what this meetup is about. But I'm just at the moment I'm just trying to solve some problems and you know, learning quickly, and yeah, and hopefully I'll be able to ask for help if I and I will probably need it on the way on this my project that I'm on. So it's my personal project that I'm on. So yeah, thank you for yeah, for the
Welcome.
having me around. Yeah.
Welcome, and pick the next attendee.
Yes. Next. How about Nimu? Nimu, are you around?
Yeah. Thank you,
Thank you.
David. Good morning, everyone. My name's Nimu. My day job is a data scientist. I work for a federal digital services consulting firm here in DC. I became a data scientist. Well, I started training about a year ago, so I've been using Python for just about a year now. This is my first DC Python meetup. Excited to be here. And I'll pass it off to Mulukin.
Good morning. Thank you, Nimu. My name is Mulukan Mujhe. I'm environmental engineer. Oh, can you hear me?
Yes, welcome.
Oh, okay. Thank you. So I'm a Python user. I use Python for data analysis and visualization. I work at NSF. Thank you.
All right. I see 4, 8, 12, 13 people. We've probably at least gone through half. Who hasn't introduced themselves that would like to?
Hi, I'm Sandra Joseph. I am a help desk analyst over at the University of Maryland Global Campus. I just started learning Python and really gotten into it, being somebody who's actually very afraid of snakes. But I actually like this program. So I like to learn it and get more in depth into data sciences. So I'm just kind of pursuing it on my own.
Awesome, welcome. Go ahead, Jacob.
Okay, I'm Jacob. I'm a computational disease modeler. Yes, these days I'm modeling COVID-19. If you have questions about that, I have to read a lot about it. And of course I have a model. I've been doing Python for 14 something years. Started doing disease modeling. It's very important to have a language like this. And a few years ago, I think 5 or 6, I started something called the Evening of Python Coding in Austin, Texas. I was in DC for a while, and Alex invited me to do it as well as in DC Python meetup. So we're having it this year as part of the DC Python meetup as well.
Very much appreciate your help.
Very much appreciate the invitation.
Okay, so for anyone who just joined, we're going around rooms doing introductions. Tell us about your use, who you are, what you do with Python. And when we get through.
Hi, my name is Kay. I work in the DC area. I work for an organization called the International Monetary Fund. I work in the IT department there. I've been using Python for about 5 years. I work a lot on like econometrics, visualization, machine learning, that kind of thing. So I think Python is really good. It has like a very comprehensive list of libraries that can pretty much do everything I need for my work. So I'm really interested in learning what I can. This is my first meetup for this meeting, so I'm really excited to be here. Thanks.
Welcome.
Hi everyone, I'm Matt. I'm just starting to learn Python, getting ready to transition out of the military, get into the cybersecurity field, or figuring out what I want to do when I grow up. So I'm trying to learn Python, and happy to be here. Thank you.
Welcome, welcome. All right, 10:15, anyone? I'm going to switch to managing, making sure everyone that needs to get in is getting in. And so we'll give it a few more seconds, and then Eric, please take it away. All right, Eric, please take it away.
Okay, you disabled screen sharing.
Oh, hang on, let me fix that. I think I fixed it. At least I clicked on a couple things in Zoom.
Okay. It does look like it. Okay, so let's get this playing. Come on. Sorry, I'm trying to get my speaker notes on my phone here, which is not connecting to Keynote right now.
Take your time. I'm still
Okay.
managing the waiting room. And for anyone that just joined, please introduce yourself and talk about who you are and what you do with Python, if you would like to do so.
There we go. Okay, so I guess I will take this away now. So I'm going to be talking about fitting big data onto your laptop using some new tools rather than some of the older tools that you may be familiar with. Now, when I say laptop, I mean that you can fit it on a laptop and not on some gigantic system. Not that I'm actually going to run everything here on a laptop because technical issues. But anyway, about me, I'm one of the maintainers for Pillow, along with Alex. I've been doing that for a while. I'm also a senior developer at Deralinx. We do open data, so data portals like data.gov.ie and smartdublin.ie. And we also do some other stuff that's not so much open data cataloging. And I'm going to talk about one of those projects here. I also do some consultant work with Alex and others. So the project that we're looking at today is called the Global Electrification Project. And what this is a project from work where we wound up doing some of the hosting and maintenance of this app, but we did not do the original development. And this is an open source system, so nothing here is actually proprietary. But at the same time, what I'm going to be talking about here is not the actual version that's deployed at this time. This project has a long history and possibly typical in the business world in that the original requirements are not the final requirements, but the project's effectively over anyway. There's no budget for any additional significant changes. The original requirements were for a largish amount of data and flexibility as to the schema and the queries and the filters that are applied to that data. The final configuration that they arrived at is one model, so no flexibility required, but there's a lot more data, many more countries, and it turns out a lot more data. So I do also want to say here, nothing in this talk should really be taken as disparagement or criticism of the original code, because really they had a different set of requirements when they were setting out, and path dependency is a hell of a drug, and you will get to places you don't want to go because you're following the logical next step until somebody can say, well, no, we shouldn't do that. We're going to go a different way. So I've got the advantage here in that I'm doing this on my own time, and I can look at this and say, we can do better than that. And my requirements aren't going to change, which is really important. So I'm going to see if I can make a better version, but first let's talk about the project. So this is currently it's a collection of a large number of model simulations for how to increase the coverage of the electrical grid in sub-Saharan Africa and other developing nations. For each country, there's about 200 scenarios, combinations of model runs. So it can cover population growth, demand growth, how the investment is done, what the expected cost of PV systems is going to be, and how they roll it out. This web application displays a subset of the results in a mapping context, so we can see where the individual clusters are and what the overall statistics are, and what the output or what the final type of electricity generation is, if it's grid or PV or mini grid or something like that. The unit of data here is a cluster, which is is kind of nebulous in that it can be it can be down to 5 people, or it can be as many as 1 million people. So like in a city, a cluster might be a lot bigger than a small village. Larger countries have up to about 1 million clusters. So when we're looking here at Nigeria, this one is a moderately large country, and I think Nigeria has about 500,000 clusters in it. And when we are looking at this, we are going over all 500,000 and summing stuff up and sending back grid types for each one of those clusters. There are essentially 3 types of questions that are answered by this. What's the overall statistics for the population, investment, and number of people connected? And then for each type of cluster, what are the statistics for the cluster type in which year? So there's an initial year, an intermediate year, and a final year. And then finally, what is the connection type for each one of those clusters? So that is data on the up to 1 million items in a country. Overall, there's about 2 billion rows in this database, and it's a 1.8 terabyte PostgreSQL instance. The architecture of this is there's a front end is a React single page app. It's statically served off of S3. That connects to a Mapbox API for all of the mapping requirements. There is a Node.js API server for returning the data about the clusters. There is the gigantic PostgreSQL database, and that's served off of RDS, and then a Redis cache for caching our intermediate results. So what are the problems with this system? First of all, it's really slow to import. The existing system is a single-threaded import running in Node.js, and it is order weeks to import data. I personally had to import about 20% of the data, and it was a week or more. One of the countries we imported took more than a day to import. It's pretty slow to query. The worst case performance through the API is on the 45-second to a minute range. And it's slow to explore. If we want to find out anything interesting about our data that we haven't already figured out, it is prohibitively expensive to query that table. I ran a simple SQL query, select distinct scenario ID from scenarios, and it took 12 hours. And I think that was even on before I imported the last 20% of the data. I haven't tried that again because 12 hours is just too much to wait for that. And because it's so big, it's expensive to host. But really, the main problem is 1.8 terabytes and 150 gigs of indexes. We've got to be able to do better than this. So the first thing we're going to look at is, what about our schema design? So this PostgreSQL instance basically has one giant table, scenarios, and it has a scenario ID, it has a feature ID, and those together make up your primary key. It has filter values as a JSON and summary information as a JSON. Now, some things to think about here. We have a gigarow database. So every byte in each row is a gigabyte of data on disk. And not only that, it's 10 cents a month to host. So for every character we have put in this row, you can just toss a dime in every month, which sucks. So the first idea here is, let's just flatten this data structure. We don't need the flexibility from JSON. JSON is great if you've got an unspecified schema, or one that you need multiple schemas for, and you don't want to change your schema along the way. So like, it would have been okay if we had 5 or 10 different models that we needed, and each one we could just shove different scenarios and features and or filters into. But that's not where we got to. So let's, and also let's look at the indexes. In PostgreSQL, we are currently running 2 indexes on this. One is on scenario ID and one is on feature ID. Now there's 2 problems with this. One is that the scenario ID is about a 15 byte string. And so we're storing that twice now, once in the index and once in the main table. So that scenario, 15 bytes times plus 4 for length, that's 20-ish. So times 4, that's 80 gigabytes of information just to store the scenario IDs. And the feature ID is an integer, so it's not as bad, but neither of these indexes is terribly selective, because each scenario ID is going to hit up to 1 million rows, and each feature ID is going to hit up to 12,000 scenarios. So we're never going to get down, the classic use of an index is to hit that index and hit 1 row. We're never going to get there with this design. So let's do a redesign on the schema. Let's take out the JSON. Let's turn all of the individual fields in the summary and the filter values into their numeric values into the table. So that actually is pretty easy. So we remove the JSON, remove the integer keys, because 150 gigs of indexes is a lot. And if you want a fast database, you want to keep it in memory. If you want a semi-fast database, you keep your indexes in memory. If you want a slow database, you keep them all on disk, and that's where we are. So let's go with integer keys, and let's do a better index. So I'm not sure if you're aware of PostgreSQL's indexing capabilities, but there's 2 really cool things about it. One is that you can use multi-column indexes. So in this case, I've taken the 2 original indexes and turned them into 1 index. So this works well in all but one of the cases that we would potentially be using the other 2 indexes. So if I'm looking for a scenario, this is fine. This will get me this will do index selects on a scenario. If I'm looking for a feature within a scenario, this also works, because I can go to the scenario and then follow that to the feature, and then I get to the 1 row. If I'm looking for feature number 1 across all of the scenarios, this does not work. The other really useful thing, and this is a total aside, is that PostgreSQL can do functional indexes. So you can index not only a column, but you can index the column in lowercase, or the column with spaces removed, or the column transformed into this other thing that you search all the time. So you can do this functional index on a column and return exactly what you want. And furthermore, you can do it in a partial index. So if you're only ever really interested in the most recent things, you can actually index something where current equals true. And then your index can be tiny compared to the rest of the system. So with that schema redesign, we got about a factor of 3 in size out of the database. So our original rows were about a K each. Now they're about 300 to 400 bytes. The index has dropped 2 because we're now using one index with 2 integers rather than one index with a string and one index with an integer. But this required an API rewrite, because now instead of querying into the JSON, I'm querying into direct columns. And an API rewrite, well, it's not trivial. It's something that could be done. So this is good. This makes it cheaper. This probably saves us about half on our hosting bill. But it doesn't really move the needle because we're still quite expensive. Like, I mean, a cloud instance that'll serve a 600 gig database with 40 gigs of indexes at any speed is not going to be cheap. We can do better than this. So what's holding us back? Okay, so PostgreSQL, the way we're using it now, doesn't use compression. So the only PostgreSQL will use compression, but it's only for large text columns and potentially for JSON columns. Now, we had JSON columns, but they were so inefficient because not only were we storing numbers in it, we were storing keys in it, but every time we queried those JSON columns, we had to cast those back into a numeric to actually do anything with them. So while we could have gotten compression out of a JSON blob, it really didn't help. The indexes are still too big. 40 gigs is a gigantic index. We still have to read entire rows when we're querying. So what I haven't told you so far is when we are doing our queries over all of the features in one scenario, we're actually only really interested in half to a third of the columns. We're still stuck in the million rows per minute range on an API query. So roughly we're looking at about a factor of 3 faster. So we went from 45 seconds to a minute to like 15 seconds to 20 seconds, which from a quality of service point of view, it's better, but it still sucks. And because of the size we're looking at and how much memory we can afford to put in a PostgreSQL server, every query here is effectively a cold read. Now, when I'm saying expensive to serve, I'm saying this on Amazon. If you actually have bought a hardware machine or renting something in colo, it's actually remarkably cheap to get something that will do this quickly. But, you know, I mean, $40 a month or, you know, about a $700 Linux machine would do it. But so we could do better than this, and maybe PostgreSQL isn't the right answer for this data set. Now, this is something coming from me. I've used PostgreSQL for 20 years. This is my favorite database. I love PostgreSQL. It has never done anything stupid for me, but it's not the right choice here. So what are our opportunities? Well, we have static data. We're not writing anything into this database, and everything is cacheable. And the biggest query is 1 million rows. Maybe we can just cache everything. So there's 12,000 base scenarios. And those could all be cached. We could write 12,000 JSON files out, serve them off of S3. We'd get, you know, 100 millisecond latency. It would be fine. But there's these filter queries where we're filtering all of the features with a minimum or maximum population or a distance to a road grid. So there's a lot of slicing and dicing that are part of the requirements. They're not the big common queries, but they're all there. So these require all the data and you have to be able to search it. And unfortunately, we need these. So let's look at different technology. ClickHouse. So ClickHouse is a columnar database from Yandex, which is the big Russian internet company. And it's designed to support a large amount of metrics data. I believe that ClickHouse was originally designed to do the Russian equivalent of Google Analytics. So they have very wide, very sparse absolutely immense databases in this thing. We're going to be using a small subset of this. So a columnar database is interesting because where PostgreSQL says the unit of how you get data out of PostgreSQL is give me a row, and it gives you a row. It's really happy to give you a row. For ClickHouse, if you want all the data across all, if you want the data across all the rows, it's actually a lot more work because it has to go through one column, grab that value, go through another column, grab that value, and so on down the line. However, the thing that makes it very useful is if you're just trying to filter on one column, you can filter that column very, very quickly because it supports the array, the SMID, the AVX extensions to search your column data. So if you have a column of integers, you can read 8 of them in at a time, run the AVX 256 compare option or compare instruction on it, and just pipeline the heck out of that thing. And it spins through those columns really fast. So it's also compressed by default. The indexes are really sparse. So for the primary keys, there are settings for this, but by default, it indexes where the values are every 8,000 primary keys or 10 megabytes of data. So the total amount of data that is in your indexes is incredibly small compared to PostgreSQL. And finally, ClickHouse natively supports partitions by lots and lots and lots of partitions. So PostgreSQL, you can partition databases, but it's kind of a pain. And they don't really recommend having more than about like hundreds of partitions. So you would think 100 is fine. 1,000 is probably not good. 10,000 is a bad idea. We've got 12,000 scenarios. That's a natural partitioning key. And it turns out for ClickHouse, that's a really good idea. So how do we get there? Well, let's look at the schema. This is pretty similar to the first cut of what we were going to do with the PostgreSQL schema. I didn't bother changing the scenario ID away from a string because it, well, I tried, but it didn't actually do anything. So we have smaller types. We have an int 8 for some of these statuses. We have float 32s. They're compressed. There's custom compression. We are actually ordering these. So we're ordering by scenario ID and feature ID. We're partitioning by scenario ID. So we'll get 12,000 directories. Or partitions. And within each one, all the data is going to be ordered by feature ID. So we can actually find the data for a feature pretty quickly. So how do we get this in? Well, so it turns out ClickHouse has an HTTP interface, and loading data into ClickHouse is really fast. We can just cat a file into a curl command that if you look at the query string there, it's just insert into scenario format CSV. And that will read this CSV and shove it into our ClickHouse database really, really quickly. And for old Unix hands, this is one of the classic useless uses of cat. So I had to have this image in here. In case you hadn't seen it earlier. So the internet is for cat pictures, so I have to have this in here. So there are some challenges with this. So ClickHouse is really picky about column types. So when you say an integer, it's got to be an integer. Like PostgreSQL, if it can cast it to an integer, it's pretty happy. But ClickHouse, nope. You can't have extra columns in your CSV. And in my case, my source CSVs are all zipped into giant archives. Unzip is single threaded, and my biggest zip file expands to 300 gigabytes. Now, that's not a huge problem. Like I can handle it, but I can do better than that. Especially in the cloud, like 300 gigs, like, you know, you can just mount a drive from EBS on that. But okay, so we'll bring some Python into this. So this is kind of half of my processing. I define some output fields. I have a way to cast into ints. I want to strip out columns or 1,000 separators because whoever generated these CSVs in a couple places, they decided that if you're going to have large numbers, you have comma separators in a CS or 1,000 separators in a CSV. I blame Excel. We also had a few scenarios where some of the feature IDs were coming in as floats, but we have to cast that out as well. So we set up a few formatters, and then one of the most fun little tricks is that Python can read zip files. So where zip is unzip is single threaded, you can run a bunch of Python processes at the same time that all read different parts of the same zip. As long as you're not writing to this zip file, you can have multiple reads at the same time. So now unzip is no longer in your single threaded zone, it's in your multi-threaded zone. And if you guys remember Amdahl's law, it's basically the more processes you have, the more your single threaded parts are going to dominate the time it takes to do this. It turns out on my cloud machine, unzip of a 12-ish gig file here took about 5 minutes, and imports through this Python without the zip took about 5 minutes. Imports with using Python to process the zip file took about 7 minutes. So it's actually quite a bit faster to use Python to do the unzipping itself. So if we look at this, what we're doing is we're reading from the zip file in its text IO wrapper. We're writing to standard out with the CSV formatter or with the CSV module. And then for each row in the CSV, we're just formatting it and writing it out. So we can add that in place of our previous cat. We now have preprocess, shove it through a curl script, and stick that in our pipeline. Python is pretty fast. So for the ones that I was benchmarking, I was benchmarking South Africa for the most part, which is each CSV is about 200 megs unzipped or 250 megs unzipped. All 216 of them together are about 12 or 13 gigs. Python can run through those in 5 to 10 seconds and and rewrite the CSVs into the format we're looking for, which is pretty darn fast. And it can do that with a lot of cores, as many cores as you want to throw into it. So we can wrap all this into a little horrific looking shell script written from Python, which I can unpack for you if you like. The one thing I want to call out here is xargs. If you guys haven't dealt with xargs much, people seem to run across it with find. You find stuff and you pipe it to xargs, and then you run a command on everything that you get. But xargs has this built-in parallelization function where you can say, run any of these in parallel. And here it's -p. So I'm running as many processes here as I have CPUs. And that will run these until it's done, and then it'll go on to the next one. This is it's a really simple way to do it. You can try doing that with Python's multiprocessing, but this is just like bam, and you're done. So we wrap that in a CSV. This has a sort of unshown download, load it, delete one, and then run that on each model using cat. So getting that all in, it's 67 gigabytes instead of 1.8 terabytes, and it's stupid fast. So the import time, 240 minutes on a C5 4 extra large to import with 16 cores buried most of the time, $3. An hour to download to my machine, $7. What's not shown here, 12 hours forgetting about the machine and not shutting it down, was like another $6. because, you know, AWS. 67 gigs of total data size, table scan in about a minute, and common queries for the API in under a second. In a little bit better numbers, that's a 250 times reduction in data size and an API response time, 50-ish times better. So these are partitioned. Each scenario is in a separate partition. I went in and looked. Each scenario is actually in its own folder or own directory. They range up to about 40 megs each. Most of them are under 10 megs. The largest storage chunk for any single column is about 4 megabytes. And for each of these partitions, the primary key storage indexes, well, storage and index is about 10 to 20K, which is tiny. So that's easy to keep in memory once you get it. So the new architecture here is we have an unchanged React single page app. We have a Mapbox API unchanged. We have a fast API server because I prefer Python to Node. And fast API lets me get stuff up and running really quickly. And then a ClickHouse database that is much smaller than the previous version. So I'm going to run through a little bit of a demo here. If I can. So let's choose I'm going to choose a moderately sized country here. Now this is running off of my local, one of my own servers, which is a pretty stout one. Where should we go? Let's actually go to Burkina Faso is a really small one. So this is one of the smaller ones. Now, most of the time here is actually I'm downloading the shape, it's not a shape file, it's a Mapbox tile from Mapbox, but it includes the outlines for all of the features. I need to, there we go. Sorry, my Zoom thing is in the way. Okay, so we can zoom in, we can poke around. So what the API is doing though is serving this data and it's serving the colors here. We can change our scenario and we get different colors, maybe. And this one is interesting. This one has hydro involved. We can zoom in a little bit. We can get the information for this one. It should tell us. So the API is responding really quite quickly. This Burkina Faso is not one of the bigger ones that we were dealing with. If I back out and go to Nigeria, Nigeria was one of the 45-second API response times. And I should see it here. There we go. And we can sort of randomly change our scenario a little bit. And if we want to filter, we can look for small population clusters. Or we can look for large ones. Yeah, so there's like one. There's one giant population cluster that is 2 million people there. Okay, so that's the web app. So let's go look at some of the data. So I'm going to run this on, so these numbers are going to run on so this is a quad Xenon with an NVMe drive and a bunch of memory. It's about $40 a month from Hetzner. So it's not like a stupid expensive machine. And if you look at this, it's calculating pretty fast. This is the query that took 12 hours on the other machine or on the other system. And we should get this in about 20 seconds, and it should say about 12,000. Oh, sorry, 30 seconds. So what if we want to do some exploring? So if we say, which of these scenarios gives the highest percentage of increased number of people with access to electricity? And I actually calculated, I wrote this earlier because I didn't think I'd be able to type that straight out. But what we're doing here is we're taking the sum of the population and who have electricity in 2030, minus the sum of the number that were connected in the base year, times 100, divided by the number in the base year as the percent connected. And then we're going to group that by scenario ID over this entire database. And this is oddly enough not a slow query. I don't know how long this would take in PostgreSQL, but this is going to take probably 20 or 30 seconds to run on this machine. And we will have an answer saying, where can we get the largest percentage gain of number of people connected to the grid? And it turns out that I don't remember that code. BI. That's Malawi, and that is South Sudan. But I don't remember which one BI is. Or we could say, what is the most effective use of money? So we have an infrastructure or investment number in here. So this is a query that says, what's the investment cost over the number of people that we connected? So what's the per capita cost to connect somebody to the grid? And in which scenario is this the cheapest? Or which 30 scenarios is this the cheapest? And I had to filter out ones where the per capita cost was below 0, because in some cases we actually they lost population in some areas in the simulation. We should get this in another 20 seconds or so, but it's a seriously fast database. Now, I do have this running on a laptop behind me. You can see the laptop back there if you were looking earlier. And this is about a 10-year-old ThinkPad. So I ran the same queries on that machine, and it's about 3 times slower. But that is a 10-year-old ThinkPad with a SATA 2 drive in it. So it's limited to 3 gigabits per second. It's, I would have demoed on it, but there's some weird DNS stuff going on with that one now. So I'm going to finish up here a little bit, and then I can take some questions. So the next thing is, how would you deploy this thing? So there's actually some options. You could stand up a ClickHouse cluster on EC2, where it would be, where you could distribute the load, and it could be somewhat fault tolerant. You could do a standalone ClickHouse on EC2 or Elastic Beanstalk. You could co-host the ClickHouse instance on Elastic Beanstalk on the same machine that you're doing the API. Now, I've actually done this for a different project where the ClickHouse database was on the order of 100 megs. And it's actually really slick because the database scales just as fast as the API does, because we can copy down the data, and anytime we deploy, we just have our new copy of the data. If we need to scale out because our machine is under load, well, we have 2 copies of the API and 2 copies of the data, and it just keeps getting bigger and bigger and faster and faster. Now, what I didn't have time to do is ClickHouse has a way to natively talk to S3 as a data source. So it is theoretically possible that we could run ClickHouse serverless on Lambda, AWS Lambda, you backing up to S3 as the data store. So if you didn't have traffic, you would basically be paying for S3 storage. And if you did have traffic, you'd be paying Lambda rates for it, which is not high. So does anyone have any questions for me? Did I leave everybody in the dust?
Somebody wrote or in the chat, it's querying across partitions, and I'm guessing yes.
Yes, it is querying across partitions. So the limits of ClickHouse tend to be more along the lines of joins rather than queries on individual partitions. So if I pop back here, each one of these scenarios, the any1, this is one partition, and this is another partition. So it's running its queries essentially in parallel across these partitions. The other thing we can do is you can actually group by, you can group across the partitions as well. So I could, oh, what's a good query for that? I mean, you could sum up the area of all of them or something like that, but that wouldn't give you a reasonable, you know, it's not a meaningful actual number. I guess what I would say is that the partitioning is essentially invisible to the user because it just looks like one gigantic table to me.
As you would expect, otherwise what good would the partitioning feature?
Yeah.
I gotta say, I've been hearing you talk about ClickHouse for at least 6 months, and I'm like, yeah, ClickHouse, but now I'm actually downloading it and trying to get it running on Mac OS, which apparently you can do. So it looks really cool.
Yeah, I haven't actually run it on Mac OS yet, except in Docker containers, because all my deployments wind up on Linux anyway. Oh, I did want to talk about this compression. So the feature ID is basically incrementing single number. So, you know, you start at feature ID 1 and it goes up to whatever. So one of the ways that one of the special compressions that ClickHouse can do is there's a delta compression and then there's a double delta compression. So delta compression takes the difference between two values in terms of bytes. Double delta is especially useful for things that are like an auto increment because it takes the difference of the differences between successive items. So in this case, feature ID, the difference would be 1, 1, 1, 1, 1. The double difference would be nothing, 0. So in some cases, this is how the feature ID storage is like 20K for 1,000,000 rows. It's because it's storing it has to store pointers every 8,000 or so, but after that, it just compresses down to nothing. It's really quite slick. And that actually saved about 10% of the size of this database. When I didn't have the feature ID compressed like that, this was more like 70 something, 72, 74 gigs. And with that feature ID compression, it got down to 67.
Well, I had a question. Is the whole stack open source except for Mapbox? That's what it looks like.
Yes. The stuff I've written hasn't been released. ClickHouse is open source. You know, all the JavaScript front end, with the exception of the Mapbox bits. Although Mapbox is the version of Mapbox that it is running is technically open source. The new version of Mapbox is not, although you do need a Mapbox key and a service and stuff like that, which is sad for open source, but like I kind of understand why Mapbox kind of closed up their source.
I have a question regarding the zip. I have a similar problem with zip. I have huge files. I need to compress them and then transfer and uncompress them. So you solved the problem of uncompression using Python, which is very interesting. What about compression?
So, well, I mean, in this case, the files were given to me compressed, and they basically stuffed on an S3 bucket for me to use. I don't know that there is a parallel version of zip, but I know there's a parallel version of gzip called pigs, P-I-G-Z, which does some interesting things.
Okay.
It's kind of it's a problem because as we get more and more cores, compression is actually one of those bottlenecks where it really works better on one core than across all of them.
Yeah. Thank you. I learned something.
All right. Hey, do you want to go again next month, Eric, and talk about Pillow? I don't think
No, not really.
All right. Well, I'll get back to you on that.
Great.
Yeah, no doubt. Thank you, Eric. Very cool. What bash was that? Oh, you want to see his bash script?
What the prompt or?
Oh, that, yeah, I was actually, that's what made me want to try ClickHouse was I think that was ClickHouse.
Yeah, that's just the ClickHouse client.
Yeah, using up the N curses like a boss.
Yeah, it's this actually I'm just Docker composing execing into it.
Sweet.
Yeah, I mean it's
everyone use. Go ahead.
It looks so much like the MySQL stuff, but I guess I don't use MySQL that much. I don't like the boxes. There are, oh yeah. So you can also do things like one difference. One difference with ClickHouse is that it's actually case sensitive by default. So where PostgreSQL will tend to like shove everything into lowercase, ClickHouse is not quite so much that way. And you can export with obviously with CSV with names. This is kind of a boring way to do it because it's only one column. But one of the other project I'm doing, I'm actually using the binary Python driver for most of the communication, but when I need to do an export, I'm actually just doing an HTTP request saying, give me this table in CSV, and I'm just passing that straight out to the client, and it's super fast, and Python doesn't have to do much to it. It's really nice.
Did I see right that it was creating the table when you pipe CSV into it?
Yeah, well, that's the import. I did have to actually create the schema for it. And this, that's the actual schema that I was using for this.
And it looks like it's pretty standard SQL for a lot of things, comparable to Postgres and MySQL and all that.
Yeah, I mean, it's got its little syntax differences. The quotes are different, and the capitalization is important. But and then the engine bit. But like, you know, the SQL that I was actually writing to do the the SQL that I'm writing to do the actual work is like totally looks like ordinary SQL. I mean, it's just a bunch of selects. And then I'm building SQL with strings, which you're not supposed to do, but I'm doing it anyway.
Oh, I did have one more question. Oh, sorry,
yeah.
guys.
Go ahead.
Eric, you said it was expensive. What are we talking about for RDS in the old version?
Okay, so RDS is 12 cents a gig a month. So 1.8 terabytes is like roughly 250. Yeah, roughly $250 a month, plus tax, plus the database machine itself. So
that's not too bad.
$300 a month. But like with ClickHouse, I could get, an order of magnitude better performance at $40 a month.
That's definitely awesome. I was just curious about.
Yeah, and the other project I'm doing with the 100 megs of data, we're doing a lot of sort of real-time checks on, say, there's a map and I want to get a summation of everything that's happening on this map for total rainfall and shocks and stuff. And I'm running that on a T2 small. I think it's T2. It's a T2 or T3 small, so like not a big machine. And I'm getting this stuff returning in 100 milliseconds. It's just, I was stunned at how fast it was. And that's a $14 a month machine that's running the API and the ClickHouse server.
Nice. And who did I interrupt, Jacob?
Excuse me?
Or somebody was asking a question. I thought. All right. Thank you, Eric. Any more questions for Eric? Otherwise, yeah, we'll have you back in a few months or mid-year or whatever. And anyone on this call or Zoom that wants to do a tech talk, please let me know. Otherwise, I'm going to find somebody for next month. And if you can help DC Python by donating, please do. Thank you guys all for attending. Thank you again, Eric. I'm going to immediately leave the meeting and upload this to YouTube. So watch for the tweet from DC Python and spread that around. Hope everyone's surviving the pandemic. Looks like we got about 6 more months of this, and I'm committed to doing, this last Saturday of the month every month. So I'll see you guys next time. And that's it. Thank you.
Okay, thanks everyone.
Good talk. Thank you. Very informative.
See y'all.
Thank you.
Thank you.